Welcome back to part two. This is part two of your week 4 geometry extension lesson. In our first part, we talked about sectors and segments. For part two, we're going to talk about what we call tangent lines. So tangent is a word that some of us have heard before. If you watch the right triangle trigonometry lesson that we did a couple weeks ago, tangent was a vocabulary word that came up there. And interestingly enough, this does still deal with right angles, but a little bit different when we're talking about tangent lines and circles. So what is a tangent line? Tangent line is a line that will intersect with the circle. It does touch the circle, but it only crosses at exactly one point. So if I had a dot somewhere off of the paper, off of the circle over here, and there was a line that I drew through that and a point on the circle. Let's say there's a line that's going to cross through these 2 points. I'll label them X and Y. So through the points X and Y. A line that crosses through the circle and only touches the circle one time at one exact point is called a tangent line. Okay, so it only crosses or touches, intersects, circle at exactly one point. So it doesn't go through the circle. It doesn't actually kind of come in and go out the other side. It doesn't pass through it. It touches at one and only one point, exactly one point. And what's interesting about this, it has a special property with the radius too, right? A radius is where I connect, again, just a refresher on our vocabulary, when we connect the center to the edge of the circle is called a radius. And no matter where I do that, the center to the edge of the circle, the radius is always the same size. So if I had an R, a radius from C to A and from C to B, they're always the same size. So if this radius was 5, then so is this radius over here. So if CA is 5, CB is 5, which also means C to Y, because C to Y, Y is also on the edge of the circle, is also called a radius. And it might be hard to tell from hand drawing these, but there's a special property that tangent lines have. They are always perpendicular, which means a right angle, right, 90 degrees to the radius. Which means if I were to draw a radius and it crosses at that point of tangency, that tangent point right here, and this is where the line XY crosses, it crosses that point Y, there will always be a right angle. It is always perpendicular here. So if there's a right angle on one side, there's also a right angle on the other side. So it is always perpendicular to the tangent line. The radius and the tangent line are always perpendicular to each other. Now, what that does for us is it brings up a couple of interesting properties, some things that we can do with tangent lines. Can we identify if they're tangent or not? And we can create some right triangles to figure that out. So let's take a look at an example, how we can use that, how we can apply that information. So if I have a circle and I have a point out here, I create a tangent line. And if I know, let's just cross that part off. So if I say that from, I'll call this X and Y again. So if from X to Y, if I know how long that distance is, let's say that distance is 4 units, I'll call it 4 meters. And I actually know how far it is from the center to Y. Let's call that 5 meters. And I want to figure out what the radius is, right? Let's say I don't know what the radius of this circle is, and I want to figure it out. And I know that XY, line XY, or segment XY, is tangent to circle C. So if I know that they're tangent, now I know now you know that angle CXY is 90 degrees. That has to be true. Because of the fact that these two are tangent to each other, that means angle CXY must be 90 degrees. So if you recall, if I have a 90-degree angle, across from the 90-degree angle is the hypotenuse, right? And we have this little formula known as Pythagorean theorem. Pythagorean theorem, which says a squared plus b squared equals c squared in right triangles, right? Do we have a right triangle? We do, because of the tangent line. Because of the tangent line, we have a 90-degree angle. So now we can use this information to solve for the radius of the circle. So the radius is one of these A and B, right? C is always the hypotenuse, right? This is always the hypotenuse. So if I know what the hypotenuse is, in this case is 5, so R has to be either A or B. So I have R squared plus 4 squared equals 5 squared. You start to simplify this. So R squared plus 16 equals 25. Minus 16 on both sides. R squared equals 9. Take the square root. R equals 3. Now, many of you might have recognized this as a 3, 4, 5 right triangle, but I know now that the radius of circle C is 3 meters using the idea of tangent lines. Knowing that it's a right angle allows me to create a right triangle, which allows me to use some of my other tools that we've already learned about with right triangles. Another way of using that same idea is to decide, are these two things actually tangent or not? So let's take a look at an example there. So if I were to give you another example here, so let's say similar type of diagram. Let's put a point out here, here. We'll call this MP circle R. Okay. So if I have MP and R, and my question to you is segment MP tangent to circle R? It's the symbol for circle with a dot in it, circle with a dot in it, R. So is segment MP tangent to circle R? Well, if I gave you some numbers here, so let's say from M to P is 11. Let's say from M to R is 13. And R to P is 6.6. So you have to have some values, obviously. And the question is, are these numbers good enough to make a right triangle? Because that's what it means to be tangent, right? In order to be tangent, this must be a right angle. And if that must be a right angle, then this must be a right triangle. Well, if it's a right triangle, then Pythagorean theorem must be true. So again, just that line of logic, that line of thinking is, if it's tangent, then 90 degrees, which means right triangle. If it's a right triangle, then Pythagorean theorem, it must be true. Okay, so if it's tangent, then it must be a right triangle. If it's a right triangle, Pythagorean theorem must be true. So let's test it. So again, the hypotenuse is always across from the 90-degree angle. So here's my hypotenuse. It's 13. So that's my C squared, right? So 13 squared should equal the other two sides added together, 11 squared plus 6.6 squared. Do some of this math. Okay, 13 squared is 169. 11 squared is 121. 6.6 squared, you might have to do on a calculator just to get the right answer. It's 43.56. Add these together. So does 169 equal 164.6? 0.56. And you should kind of see that, right? The decimal here, there's no decimal over here. And since these are not actually equal to each other, so it's not equal, therefore not tangent. Okay? If they're not equal, then they're not tangent. So if the Pythagorean theorem gives you a false statement, which this is a false statement, 169 does not equal 164.56, then then the circle and this line are not actually tangent lines. This is not a true tangent line. One other property that we're going to go through, and then that'll be it for our tangent line discussion, is what if I had two tangent lines that started at the same point off of the circle? Okay, so let's draw an example here. So you have our circle, and let's say we had a point out here. So circle R, we'll call this point P. So if point P interacted two times with lines that are tangent to the circle. So let's say we have 2 points here and another one over here. We'll call those A and B. So we're given that these are tangent lines. So we know that segment AP and segment BP are tangent to circle R. Again, remembering what this means, that they only intersect or cross that circle at that one spot, and then they keep going on and on forever without ever interacting with the circle again. So if these are tangent, then they create that 90-degree angle, right? If I were to kind of connect them to the radius, it would be a 90-degree angle here. But what happens if two tangent lines, so we have two tangent lines with a shared point not on the circle, then the lines, the segments, are congruent. Means that they're going to be the same distance, right? So that means that from A to P is going to be the same distance as B to P. So if I told you that A to P is 10 feet, then B to P is also 10 feet because of this property. All right, so this is another property of tangent lines. So if you have two tangent lines with a shared point that's not on the circle, then the segments that are created there are going to be congruent to each other. So let's take a look at one example with that property, and then we'll get you out of here. All right, so I've got two lines that are tangent to the circle, two segments. Let's call this B, I'll just call it A, B, and C. So I know that segment AB and CB are tangent to the circle. And I want to solve for the distance. So find CB, find the distance of CB. So we need to have some values in here. So let's say that from C to B is x plus 5, and from A to B is 2x minus 12. Well, again, because I know that these are tangent lines and they both originate at the same spot B, I know that they have to be congruent to each other, those two pieces. So what that means is that x plus 5 has to equal 2x minus 12. If I solve this for x, so I'm going to minus x, and I'm going to add 12. This gives me 17 equals x. I know 17 equals x. CB is x plus 15. X plus 5, not 15, x plus 5. So I get 17 plus 5. So CB is 23 units. And that is how we can use the idea of those two tangent line segments being congruent to each other to help us solve for a missing value. There are a lot of other applications here of, what if we drew other shapes in here, or what if we connected the radii? You're going to get some practice with some of those. But these ideas of knowing that those are congruent and then trying to take that to the next level of the applications is something that we'd like you to try to do. If you have any questions about those types of problems, you run into an issue, please don't hesitate to come see office hours or email me. Let me know what's going on. I'll be happy to help you out with any of those types of problems. So hopefully these help you out a little bit. Don't forget to watch part 1 on sectors and segments. They'll help you out for this week 4 extension lesson as well. So take a look at that on the YouTube page. And hopefully if you have any questions, you'll reach out and you'll be able to use these lessons and examples to complete those extension worksheets. Have a good rest of your day, and we'll see you next week for our next extension lesson.